All right, 4025 MA mechanics tutorial number 10. I remember we did general plane motion that encompasses curvilinear translation and at the same time also rotation of rigid bodies around the fixed axis. Let's start with level 1. I put here some definitions and reminders. So first of all, these are the equations of motion of 2D plane, the most general equations of motion. So these are for translation and this is for rotation. This is a vector equation and this is not, because we are in 2D, so we have two translations and one rotation. And also a reminder of some kinematics of curvilinear translation, which is very, very important. So you should know what V, omega, AT, alpha, AN, and R are. So let's start. So we have, if the coefficient of static friction between the tires and the road surface is mu s, so mu s is coefficient of static friction, determine the maximum speed of the 1500 kilogram car without causing it to slide when it travels on the curve. Also neglect the size of the car. So we have this curve, which is a radius of curvature of 200 meters. And this car is going on a curve. So let's start with the free body diagram. So I will draw the curve. Something like this. We know that the car is here. And we know that there is a certain radius of this. There's a certain curvature radius. Rho. And now how many forces are acting on this car? Well, of course, we know that there is the weight of the car. Now the weight of the car is acting inside the plane. So of course, we are looking at the car from the top. So the weight goes inside the road in this case. So and the normal force is coming outside. So if you look at the car from the side, look at the car from the side, you have that the weight force mg and the normal force n are acting like this. This better. Yep. What other forces are acting on the car? Well, of course, you know that the friction force on the tires is the force that makes the car turn. Now, that's the most important thing. This is the friction force from the tires. And that's the only force that is allowing the car to actually turn. Okay, so let's remember what is a friction force. Friction force, of course, is coefficient of friction times normal force. Now, how do we do, which reference system do we use? Of course, we don't want to use X and Y because it's very complicated. If we use X and Y, horizontal and vertical, if you look at this, it's very complicated because now the acceleration is going in this direction and this direction, so which are not aligned with X and Y, so it's very complicated. So instead, we are going to use the inertial reference frame T and B. So T is always in the direction of motion of the car. So of course we see that the car is going up. So T is this one, tangential to the path in this direction. The N axis is always perpendicular to T, and it's in the direction, of the is going towards the center of curvature. And finally, B, in this case, is binormal and is going outside. So B is in this direction. B is going outside of the plane in this case. So if you use this, we can split the forces. So sum of forces along T is the mass times tangential acceleration. Sum of forces along the normal direction is the mass times the normal acceleration. And remember, since we are not leaving the path, sum of forces along the binormal direction is 0. This is last week's. So let's just explicitate these three. And we have sum of forces along T. There is no force along T. So let's say that 0 equals mass times, what is the AT? Remember, AT is alpha times R. In this case, rho. That's the radius of curvature. I called it rho. And so we have that there is no angular acceleration of this car. And this is exactly what we expect for a car that is going at constant speed on a curve. It's not accelerating tangentially. But since it's curving, it must be accelerating normally. So this normal acceleration is non-zero. So let's say, let's check how many forces we have in this direction. It looks like we only have this, which is exactly in the same direction as n. So this is positive. So we have mu s times n equals mass times normal acceleration. Now the normal acceleration is either this one or this one. Now, of course, since we do have information on v, no, we want to find the information on v, determine the maximum speed that we need. We are going to use the second one because it contains the information we want. So it's v squared divided by rho. How many unknowns we have here? We have, this is 1 and this is 2. So of course we can't just solve this by itself. We have to also write the other one. The other one says that if you look at this, normal force is mg. Normal force is just mg. So now we have only one unknown in the second equation. So I can say that the second equation becomes mu s mg equals mv squared divided by rho. And lo and behold, what we found is that this is independent from the mass. So it doesn't matter how much the car weighs, if it's a car or if it's a truck or if it's a bicycle, doesn't matter. It's the same friction force that you need. So this speed, this maximum speed you can have, v, is the square root of mu s rho g, g rho, g times rho. So this maximum speed, we call this v max, only depends on friction coefficient. Static. It depends on the gravitational acceleration. Depends on the radius of curvature. So if you want to have a, so of course, if you have a narrow curve let's say if it's a very sharp curve like this, then the radius of curvature is smaller. And so that means your maximum speed will be smaller. And again, if you have a lower friction coefficient, of course, your maximum speed will be smaller as well. So in order to maximize this speed of which you can take the curve, you need to have more grip or engage in larger curves. So not very sharp curves. Okay, so we can just since we know everything about this, we just need to do the calculation, and the calculation should be 22.1 meters per second. Let's check the units. This is the square root of meters per second squared times meters. So it's meters squared per second squared, under square root is meters per second. Checks out. All right, now let's solve exercise level 2. We have a 50 kilogram projectile traveling in a vertical plane with a speed of 40 meters per second. So we know this is the path. Again, we don't care about the path itself, because we know that at this instant of time, at this point here, where the bullet is, it's traveling with a certain speed, v, of 40 meters per second. Let me do this in gray because I don't want to include this in the free body diagram. Don't include the forces in the free body diagram, the velocities in the free body diagram. Never include it in the free body diagram. We want to determine the tangential component of its acceleration, so the AT, basically, and the radius of curvature R, rho in this case, of its trajectory at this particular instant. We know that there is a 30 degrees angle, so this V in this case is angled at 30 degrees, and it's in the tangential direction. Okay, so again, this is another way of saying free body diagram. So how many forces are acting on this? Anyone? I'd say one. There's only one force acting on this, and it's the gravitational force. So the weight of the bullet itself. So mg. And are we using, since this is on a curved path as well, so we are also using here, use T and B, so the inertial frame. In this case, we have T, since the projectile is moving in this direction, T is this. Tangent. And N is, of course, towards the center of curvature. And perpendicular. Now we have the question on how to write the equations of motion. Equations of motion are always the same. So we are using, we don't need B. There is no force in the B, that direction. So there is no force perpendicular to the plane. So we don't care about the third equation. Just spell out the first two equations. Sum of forces along T is mass times tangential acceleration. Sum of forces along N is the mass times centripetal acceleration, normal acceleration. Of course, this mg here, this mg, let's write it down here. This is mg. This force mg has a component along N and a component along T. this should be perpendicular. So this mg here has this component along t and this component. No, sorry, this component along n and this component along t. Now, the angle is 30 degrees. We just have to find if it's this angle here or this angle here. So where is my 30 degrees? Of course, this is 30 degrees. This one is 30 degrees. Therefore, so 30 degrees is made by t and the horizontal. This is vertical, so it's made by mg and n. So this is my 30 degrees. Therefore, this one is mg cosine of 30 because it's adjacent, and this one is mg sine of 30. So let's explicitate these equations by saying the only force in direction t is this one, which is minus mg sine of 30. Equals mass times, do we need alpha r? Well, the system is, the problem is requiring the tangential component of acceleration. So we just leave it as 8t because that's what we want. And the second equation is, of course, this is in the same direction as n, so it's mg cosine 30 equals mass times, what do we want here? We know v and we want rho, so let's use this expression, v squared divided by rho. So v is given, it's 40 meters per second. Let's check the unknowns. This is unknown, everything else is given. Also, let's find out that this mass is not required anywhere. So the mass of the bullet, it's useless, but it's required because we know it feels the gravitational effect. Because otherwise there would be no force acting on the bullet, and this bullet would be going straight. And that's it. Yes. So this is unknown number 1. Unknown number 2 is this. So it's two one equations in one unknown that we can solve independently. So I can finally say that 8t is just minus g sine 30, which is half of g, which is equal to minus g divided by 2, which is 4.9, something like that. Yes, minus 4.9, of course, because it's minus g divided by 2 meters per second squared. And rho equals v squared divided by g cosine 30, which should be equal to 188 meters. There you go. This solves this problem. As you can see, it's very easy, quite straightforward. Once you know, I mean, the hardest part is always making sure that you understand the free body diagram, how many forces, and if you have to use usual x and y coordinate frames or the t and b. Nabu is asking, if I don't put the minus, would I be wrong? Yes, because this has a meaning. This means that the tangential acceleration being negative, it means that the bullet is decelerating. So it has quite a strong meaning. Okay, you will not lose all your marks, but you would be wrong. So some marks would be docked out of the solution because you have not found out the full story of this projectile. Okay, so make sure you understand this direction here is against t, and so you need the minus sign in the equation, and then it gets translated into a minus sign in the tangential acceleration. Let's do exercise level 3. I mean, it looks like it's more of the same, but it's quite different this now. The sports car having a mass of 1700 kilograms travels horizontally along a 20 degrees banked track, which is circular. It has a radius of curvature of 100 meters. So this is what's going on here is this. So we are on a circular track. Oops. Let's center this. Oops. This is the center of the track. And let's say we are here. This here, let's say we are here with the car. So the radius of curvature of this track is this one. Rho. The coefficient of static friction is μs 0.2. The mass of the car is 1700 kilograms. Theta is 20 degrees is here. Rho is 100 meters. We want to determine, again, it's exactly the same. We want to determine the maximum constant speed at which the car can travel without sliding up the rope. So we want to find Vmax. Again. It's the same thing. So we also need to know, we also need to do the free body diagram of this car. So the free body diagram, let's use T, N, and B. So the reference frame is, again, T, N, which goes in this direction, and B that goes inside the plane in this case. And this is not sufficient though, because we want to also, this free body diagram here is not sufficient because we also want to see what happens along this other plane of the car. So let's do two free body diagrams of the same thing. So this is the car. This is theta. So how many forces are acting on this car? Of course, there is the weight force, mg. There is the friction force, ff, that is keeping it from sliding. And we have the normal force here from the ground, from the truck. I think that's it. This is the center of the car. Let's also draw this one here. Now, T is coming outside of the plane from this point, because say the car is going in this direction in front of us, so it's coming towards us. N is not in this direction. See, if you look at the top, N is in this direction. And so if T is coming outside and then is going here, the binormal is normal to both of these. So the binormal is up. So as you can see, the difficulty here was all about finding what is the reference frame, because now everything is given and we just can solve the equations of motion. Easy. So let's draw the equations of motion. We need 3. Sum of forces along t equals 0. Sum of forces along n equal, sorry, not 0, is m times acceleration of t. This is m times acceleration of n, and this is sum of forces along b. Since it's not leaving the track, there is no acceleration outside of the track, outside of the plane of the track, Tn. Okay, so let's go in the free body diagram and let's find what's going on here. So unfortunately, all these forces, only mg is along b. Ff must be split along n and b. N must be split along n and b as well. So we have to do some calculations for these. So this is Ff. So Ff has a component along b and the component along n. Along b, it's this component here. And along n is this component here. This is Ff. Let's say this is, we know that Ff is also mu s times n. So this component, this is of course 20 degrees. You should agree with me. This is theta. Let's call it theta. So this is opposite to theta, and we have mu s n sine of theta. And this one is mu s n cosine of theta. Regarding n itself is in this direction here. And then this also has two components, one along n and one along b. One along b is this one along n is this one. This one is, let's check what's the angle first. Now n, this angle is made by n, the normal axis, and ff. Now this is normal to ff, and so the same angle is made with the normal to n. So this angle here is 20 degrees. This angle here is theta. You should agree with me that this angle is theta. And so this angle is theta. Therefore, this is n sine theta, opposite, and this one is n cosine theta. All right. So now now that we have everything, we can just solve. Let's explicitate the equation. So from here, I have, there are no forces along t because it's not accelerating. Since we have no forces along t, let's do, let's say 0 equals 0. So there's 0 equals m alpha r, so alpha is 0. This is what we expected. There is no acceleration along the track because the car is going at constant speed. Do I call it R or rho? I called it rho. So let's call this rho again so we don't get confused what it is. The second equation is sum of forces along n. Along n, we have the component of ff and the component of n itself. So they are both positive. See, n is positive leftwards, and this is left, this is left. So they're both positive. And I would say mu s n sine theta, sorry, cosine theta, plus n sine theta equals m v squared divided by rho. Let's check how many unknowns we have here. This is unknown, and this is unknown. So we have one equation in two unknowns. So we need to write the other equation, because the other equation contains information on n. N is mu s n sine theta is negative. Sorry, I think that b is going in the opposite direction though, but it doesn't matter. Mu s n sine theta is down, so negative. N cosine theta is up, so it's positive. So n cosine theta and also mg. Mg is also along b. So we have three terms here. The terms are n cosine theta minus mu s n sine theta minus mg equals 0. This is the other equation I need. And in this equation, I only have one unknown. So first I solve 3, solving 3. So this is equation 1, 2, and 3. Solving 3, we get n equals. This should be mg times, no, divided by mg divided by cosine of theta minus mu s sine of theta. Should agree with me, this is n. Yes. And finally solving 2. Now this is a number in newtons that we can find out later. And finally solving 2. Solving 2, we have that v squared, sorry, v, which is what we want, v max, is mu s n cosine theta plus n sine theta divided by times rho divided by n. Since we know that n is mg, so on and so forth, this m also doesn't matter. Very good. So this is a number in meters per second. And I believe that this number is 24.4 meters per second. Any questions? No, doesn't look like so. So let's solve exercise level 4, which is a vehicle designed to combine the feel of a motorcycle with the comfort and safety of an automobile. The vehicle is traveling at a constant speed of 80 kilometers an hour. So let's say that V is 80 kilometers an hour along a circular curved road of radius rho 100 meters. Determine the tilt angle of the vehicle, this theta here, so that only a normal force from the seat acts on the driver. So we're talking about the driver here, not the car itself. Neglect the size of the driver. So if you do the free body diagram of the driver, which I will just explicitate as a large point, this is the driver. we have that the driver is going up. This is also the same thing. So the T direction is coming outside of the paper. And so the normal, so the car is curving around this curve, and this is B. Now B is going down. Okay, because if T is coming out and then is going left, then B is going down using your right-hand rule. So it's T towards you around N. So if you put T onto N, you end up with B down. So this is the reference system. I mean, it doesn't matter if you put B up or down, because previously this should also have been down for the same reason, but I put it up, and as you can see, it doesn't matter. But by convention, it should be down, because T over N gives you the direction of B. Remember, the direction B is given by T cross product N. So this is what you should remember. So T is coming out from this point here, N is going left, and B is going down. What we have here is that only the normal force, as we said, only the normal force must be taken into account. Because the driver is experiencing no force other than a normal force from the seat when it is curving at constant speed. Remember, we are going at constant speed in this case. Now, of course, the driver also feels its own weight. That makes sense. mg. So let me take this here, all of this here, this here, there you go. So that's, the equations are always the same. We need 3 equations, for which the first one is useless in this case. Zero, and also let me explicitate these as alpha rho, and since we want again V, I'll use V squared divided by rho. Since we have rho. Now the only thing that is left is to split this only force that is neither along N, neither along B. So let's do N, this is N. This is N. Then N as a component along N, and the component along B. This theta is unknown, so this is what we don't know, unfortunately. So this angle is unknown. And that also means that this angle is unknown. This angle here is also theta. You should agree with me. Doesn't look like, that doesn't look nice. Good. So if this angle is theta is this and this, which is this and this. Therefore, theta is this angle. So that also means that this thing is n cosine theta, and this thing is n sine theta, opposite adjacent. So let's explicitate our equations again. One more time, we have here. No force in the t direction means m times alpha r means that alpha equals 0. Okay, we don't need this, but good to know. In the n direction, we have the normal force as a normal component, which is positive. So n sine theta equals, and that's the only force. So n sine theta, the only force in the n direction. So n sine theta equals m times v squared divided by rho. And in this other direction, in the b direction, we have mg minus n cosine theta equals 0. Now let's label this equation 1, 2, and 3. Now we want to find theta. Now theta is my unknown. My unknown is theta. I know v, I know rho, and then the normal force is also unknown. So the normal force is unknown and theta is unknown. Now, since we don't want the normal force, we only want theta, I'm going to, let's divide uh, 2 by 3. So to get rid of n. And also I would like to rewrite this one, this equation 3. Let me rewrite it in another way. So this one is n cosine theta equals mg. So otherwise it looks like we are dividing by 0, which is very odd. So I'll divide the left-hand side of 2 by the left-hand side of 3 and the right-hand side of 2 by the right-hand side of 3. This gives n sine theta divided by n cosine theta. As you can see, n and n go away, equals m v squared divided by m rho. As you can see, also m and m go away. So this goes away, and this goes away. So we are left with an equation that is, of course, sine over cosine is tangent of theta, which is equal to, am I missing a g? Yes, I'm missing a g here. Divided by mg rho. So v squared divided by g rho. And that also means that theta is the arctangent of v squared divided by g rho g rho. Let me say rho g because it sounds better. And this is equal to, this should be equal to 26.7 degrees. Now, the only thing that possibly might put you in trouble is that the velocity is given in 80 kilometers an hour. So remember, to use the correct units. So 80 kilometers an hour correspond to 80 times 1000. And this is 80 kilometers an hour divided times 1000 meters in a single kilometer divided by 3600 seconds in an hour. Okay, this gives you certain number in, as you can see, this goes away. So this and this, sorry, this and this goes away. This and this goes away, and we are left with meters per second. This is meters per second. Okay, this should be easy enough. Last one. This will take into account rotational dynamics as well, because this disk is spinning. And we have to also make use of the rotational dynamics things. As I set this up, as you remember, let's do this later. Here's a disk, and let's say this is X, this is Y. You know that IZZ here is 1/2 mr squared, where this r is the radius of the circle. Okay, so the disk has a mass of 20 kilograms. It's spinning at the end of the strut with a certain angular velocity of 60 radians per second. So let me draw the free body diagram of this already. Want the free body diagram of the disk itself. So this is the disk. And this is the center of the disk, which is of course pinned. And there's a strut around it. How many forces are acting on this disk? Of course, we have the weight of the disk itself, mg. We have the force from the strut. Now this is pinned here and is pinned here. So this is a truss member. Basically, it's a rod. So you know that the force must be in either of these directions. Let's call this reaction from the strut. And finally, we have some friction coefficient here. So we have rough contact against the wall. Rough contact means that you have a normal force on the wall, and then you have a friction force here, FF. These are all the forces acting on this disk, and we need to find the time required for the motion to stop. Let me put the velocity here. The velocity is not part of the free body diagram. That's why I'm using this very dull colors, just to remind me that this is going at 60 radians per second. On the free body diagram, you don't use velocities, you just use the forces. Mu k is given. 0.3. The mass is 20 kilograms. Okay, so this is B, this is point B. And let's start. Now, in this case, we have to make use of all the information that we want, that we need. So the sum of forces. Now, in this case, we can use X and Y. I don't see why not. Because this point B is not going anywhere. So point B is not moving. This disk is just rotating. So these translation equations will be useless. But again, since everything is almost horizontal and vertical, let's use now the XY axis. Probably easier to use. And so I know that sum of forces along X is mass times the acceleration of B along X. Acceleration of B because B is the center of gravity of the disk. Sum of forces along Y is the mass times acceleration of Y of B. And finally, the sum of moments around B is IB times alpha. Now, let's explicitate these first two. These first two equations are for translations. Let me say here, this is translations. This one is rotation. So explicitating this gives me this R can also be split into its vertical component. And the horizontal component. Do we have the angle of the strut? Yes, we do, 60 degrees, very good. And 60 degrees is this angle here. This one is R cosine 60. This one is R sine 60. Everything else is horizontal or vertical. That's very good. So let's start with the horizontal forces. We have R cosine 60 going along X minus the normal force of the wall is 0. In this case, we have two unknowns, R and N. So we still can't solve this. Let's see if by adding an equation, how do I know that this is 0? Well, this is 0 because, again, I told you that the center of gravity is not going anywhere, either in the x-axis nor the y-axis. Center of gravity is fixed. So it's not accelerating. Finally, for this equation y, we have r sine theta, sorry, r sine 60 minus mg plus ff. Remember, ff is always, in this case, mu k times n. So plus mu k times n equals 0. Again, 0 because it's not going anywhere. And lo and behold, we have the same two unknowns. So we can solve equation 1 and 2 as simultaneous equations to find R and N, which again are not required anyway, but it's good to have them. The last equation is the sum of moments around B. So how many forces are giving moments around B? Now this one is passing through B. This one is passing through B. This one is passing through B. So the only one that is not passing through B is the friction force. And what is the moment of the friction force around B? It's a positive moment because it's counterclockwise. And it's FF times the radius. The radius, do we have the radius? Yes, 150 millimeters. Let's call this small r, 150 millimeters. And so mu k, it's positive, as I said. So mu kn is the force times the radius equal, that's the only force that gives moment. IB, what is IB? IB is IZZ in this case, because it's exactly, this is point B, so this is exactly IZZ. So 1/2 of the mass r squared, it's the same r of the radius, times alpha. Let's check how many unknowns we have here. We have the second unknown, and the third unknown here. There you go, everything else is given. So first we need equation 2, 3. So this is equation 3. So first, solve. Let me see, can we get rid of r? Yes. No, not in an easy way. So we have to solve equation 1 and 2. 1, 2, to find n. So let's solve 1 and 2. Well, let's not solve it. This is up to you. You solve them. You solve equation 1 and equation 2 to find R equal whatever and N equal whatever. This is Newtons. Finally, find alpha from 3. So you solve alpha equals something radians per second squared. And now what's asking is, what this is asking is the time required for the motion to stop. So now that we have alpha is constant. Observe, alpha is constant. Thus, omega of t, let's call this alpha 0. And so integrating, you have that omega of t is alpha 0 t plus omega 0. And this omega 0 is exactly this, because this is the starting omega. Okay. And so we can find what is the time to stop. So this equation here, I can say, let me put these here. So I can say that the time to stop is the time that it takes for omega to be 0. So the equation, let me rewrite the equation first. Equation 0 equals alpha 0 times the time to stop plus omega 0. And so that means that, this means that the time to stop is just minus omega 0 divided by alpha 0. Yes. It looks like we have a negative time, but we don't have a negative time because alpha is a negative number. How do I know that alpha is a negative number? Because alpha is, alpha is a positive number. It's omega 0 that is a negative number, because omega 0 is clockwise. Omega 0 is clockwise, so it's a negative number. Yeah, so this looks like a contradiction, but it's not. It looks like it's impossible, but it's not. And let's have a look if it's in seconds, and it is in seconds, because radians per second divided by radians per second squared, it's seconds. So that makes sense. Okay, any questions? If you don't have any more questions, I'm going to stop recording right now. So thank you for attending.